Oh, hey, it's time. Welcome back, folks. So this is our second exam week. Today we're going to finish covering section 11.2, and there is not a new assignment since I think it turns out putting out an assignment where you're expecting feedback from before you get to the exam is pretty hard to do when the exam is before the due date would have been. So instead of assigning problems to be turned in, and you can turn them in if you'd like, just for the feedback, I assigned purely just odd problems that would be similar to exam type problems. You could consider this a list of extra sample exam problems for section 11.2. And since our exam is on Thursday, 11.2 we're just about to complete, is a pretty short turnaround time. The 11.2 problems that we do put on the exam are going to be kind of more straightforward versions. So it's not going to be anything too wild, and this list is a very spot-on kind of list for directed practice. Any questions about that? Okay, other announcements I have are that the sample exam 2 problems finally got updated, and the update is purely just the section on the very top. So if you do not necessarily want to print out the entire document, you'd be saving a lot of paper. This would be the only change. So you can say maybe print page 1 if you like. And once again, this is just a set of odd problems. This list is maybe different from the other list. I just picked problems that looked like great exam questions. So it's not necessarily the same list, but there's probably decent overlap in there. Let's see, 45 looks like it's on both lists. Looks like that's a really good problem. But other questions then about that? Okay then, so our plan for the week is we're going to complete 11.2, which will be the end of the material for the second exam. On Wednesday, we'll have our second review, and you folks are very encouraged to bring any kind of questions that you have, whether they're homework questions, questions on the sample exam, questions on, say, other problems that you're looking at. I'll be happy to use those as discussion for the class. Also, just in case, I'll bring my own material as well to help direct our review. I think that's the end of the announcements. Any questions at all? Okay, so let's start with section 11.2. 11.2, we did a couple things on the end of Thursday, which was, it feels like a long time ago already. The two things we did was we first defined what it meant to say a series. It's defined in terms of the original sequence, and what we're trying to achieve, if there's a mathematical way to do it, is add every single term of the actual sequence. We could just stop here, but for emphasis, we added the nth term and say, keep on adding forever. We're going to try to put a number to that in a mathematically reasonable way, and that number would be lowercase s. We're going to take the limit of the sequence of partial sums, which is another series in its own right, defined as this for this nth term. If the limit here exists and it's finite, then we'll say the entire series has value s. In other words, we'll have achieved a way to mathematically add infinitely many different terms and get a number out. And they're not necessarily all 0 because that's cheating. So then we can say, if this limit exists and is finite to value s, the series itself would converge to s. However, if the limit does not exist, and that sometimes happens, that's what we mean for the series itself to diverge. So let's start with a couple questions or a couple warm-up problems. But any questions first? Okay, one question that can be very tricky, which is in a couple of those lists up there for practice problems, goes about like this. It says, suppose the sequence a sub n, or we could just leave it like this if we're trying to save ink in a book or chalk on a chalkboard. You could go from n equals 1 to infinity if you like for further detail, but sometimes it's just indicated in this way. We'll say, suppose that the sequence satisfies the limit as n goes to infinity of s sub n is equal to 7, where s sub n is the associated sequence of partial sums. So that's a problem so far. What's weird about the problem is nowhere does it actually say what the definition of the sequence a sub n is. We just know that there is some sequence. There is a sequence of partial sums associated to it, defined down there, where Sn is the first term plus a second term all the way to the nth. And we're told that the limit comes out to 7. even though I don't know what that sequence is either. So really this is kind of a vocabulary or concept type question. The problem then goes on to say, determine if the series A sub n converges or diverges. It says even more, if it converges, find what it converges to. That's a pretty wordy problem. I think it's an important problem and a pretty decent exam type question where it's really just a concept type question trying to attack that very large definition. And once again, these are slightly weird ways to write series and sequences, but it's just a way to abbreviate. If you're not a fan of that, you can always add extra symbols to be specific that the sequence goes from 1 to infinity, which forces the series to go from 1 to infinity, and the sequence of partial sums to go from 1 to infinity. But we're writing things in slightly different notations because all of them are very common, and it's good to train your eye to see this without the red and see it with the red for the same quantity. So that's a problem so far. Any questions to that step? So I have a huge definition to the right, a really, really long problem to the left, but it's an important problem and pretty decent as far as exam questions go. First question we can ask ourselves, does it converge or diverge, the series itself? Yeah, it ought to converge. If we go back to the huge wordy definition, I mean, we really can't make it shorter. It says the series would converge provided the limit here exists and is some finite number s. So here we do have the sequence of partial sums converging to 7. So this shows since the limit as n goes to infinity of s sub n exists, this series, as I goes from 1 to infinity, of a sub n converges. Because we said it converges, we have an extra step. The question now is, well, what would it converge to? And we can write the summation as I goes from 1 to n of a sub n would converge to 7 itself. And that's the second part of the definition. It says if we have the sequence of partial sums, limit exists, if it converges to some finite number we call lowercase s, then the series itself takes on value s. And we say it converges to that quantity, or just write that the summation as I goes from 1 to n of a sub n is 7. In other words, for that problem, we can put the number 7 to it. Any questions about that problem? Really more of a concept type question once again, because we did not actually have any sequence there. So let's redo this kind of same problem with a different kind of series. Any questions at all first before we go to a new example? Okay, so this example is really just to warm ourselves up to the working definition for really the majority of the entire chapter 11, of which there is 11 different sections. We're only on the second one. Second question is going to say to determine when the summation as I goes from 1 to n of, let's make this be a times r to the power of n, converges and diverges. So I've done a couple things in this problem. We have another series, which implies there is a sequence. So I'm not entirely sure what that sequence is because it depends on the variable r itself and that constant or coefficient a. But at least we have something, a little bit more than what we started with on the previous problem. We're going to say, based upon what conditions for r will we have convergence, divergence? In fact, a doesn't matter because a is constant, and if there is convergence, you could factor 8 outside of the entire series itself and only be concerned about this much. But we'll leave it in as it's tradition. So really our job is to say, what values of r will we have convergence and what values of r would we have divergence? So let's do that next. Any questions first? Okay, so if we want to determine the convergence or divergence, really it comes down to this. When does the sequence of partial sums converge on a specific real number? So if we want to address this problem, we really just need to write out S sub n, the nth term of the sequence of partial sums. So let's do that next. First we can say the associated sequence is really inside here. It would be a sub n, as n goes from 1 to infinity, set equal to, we'll let I be 1. Well, let's do a slight adjustment there, just for the sake of maintaining the same type of formula that you'll see in the book. Let's put a -1. I'll highlight that small change in red. It really makes all the difference because there's two versions of the formula depending on whether you did throw in a -1 or did not. So let's go with this as the book does. Everything will be consistent. If we let I be 1, in just this much, we would have a, since this would be r to the power of 0. If we let I go to 2, it would be a times r to the power 1. If I goes to 3, the next term would be a times r squared, and so on. So that's the pattern in the sequence, which will continue forever. But remember, this implies we're trying to take all these portions, put plus signs between them, and see when this comes out to some number. But at least we have the sequence. Then we go to the sequence of partial sums, S sub n. So we're getting there. Any questions before we go to the partial sums themselves? Okay, in the partial sums, we have the sequence of partial sums is defined by, well, there's loads of ways to define the sequence. We could use this formatting right here if we'd like, or we could just specify the formula for the nth term. That's just easier to work with in a lot of problems, particularly this one. So let's go with that route. It's defined by the nth term would be, well, we go to a1 plus a2 plus all the way to a sub n. But those are precisely these values here. So we can say S sub n would be the first term, a, plus the second term, ar, plus the third term, ar squared, all the way to the final term, ar to the power of, this feels weird, but it would be power n minus 1 because we have n terms and we had power 0 at the first term. So that's the sequence of partial sums, Sn. Any questions about it so far? Yeah.
You always put the -1?
In this specific situation, I would, but that's only because of the specific format of the formula that we're going to look at. What we could have done, what I wanted to do, is go like this because it just feels better to me. If we wanted the same formula, we'd have to re-index. Oh, sorry, that should have been infinity. We were looking at that. We could re-index at 0 and make it the same quantity.
Oh, okay.
If we start at 1, it should be at n minus 1. Other questions so far? Okay, so what we need to do is, we need to look at the limit of this whole mess right here. So we need to determine when does the limit, as n goes to infinity, of S sub n converge, or when does it diverge? Or when does the limit exist or not exist? So that's where we're at. That's a tough limit, it turns out. But if we do a bit of algebra first, it's not so bad. So let's do that over here. So this is the work for the limit, and by the limit, that one that we're leaving hanging for just a moment, we can take S sub n, which is equal to a plus a to the power r, a to the power of r squared, all the way up to a to the power of r, 8 times r to the power n minus 1. So that's S sub n, and we're going to do a bit of algebra on it. So one thing that's really annoying about this is the n minus 1. So one thing people sometimes do is, let's just take r times S sub n. If we did that, we could distribute r into every single one of these terms, and this would become r to the power of n. So the new thing would be a times r plus ar squared plus ar cubed all the way to a times r to the power n. So that's r times s sub n. Now we have two different partial sums we're looking at, one multiplied by r. Any questions to that stage so far? Okay, and kind of the motivation or the reason for the next step, the idea of it, is we're looking to try to copy what we did with the telescoping sum that we ended on with Thursday. When we had a telescoping sum, we were able to cancel a whole lot of terms. We don't really have a telescoping sum, but if we work with this, we could produce one. So say, for example, the next algebraic step we could take could be something along the lines of take s sub n and subtract r times s sub n and see what happens. Then there'd be a tremendous amount of cancellations. For example, the first term in s sub n would be the a here, and we're subtracting off every single one of these terms. So you would get an a. The next term is ar, but we're subtracting rsn, so there's a cancellation from here to here. And those cancellations propagate all the way until the final term. Does that make sense so far? Okay, so we're essentially taking this list, subtract the second list, and remember like terms are off by 1, so this would cancel here to here. We'd have cancellations all the way to ar minus 1 and the prior term to this one, which is ar minus 1. So the cancellations would go essentially like this. Ar to the power of n, however, is not on this list, so it survives. We're doing negative rsn, so it's minus ar to the power n. And that's where we're at so far. Any questions to that step on subtracting the two lists? Okay, remember though, our goal is this limit. So what we produced by a bit of algebra that required ideas from the telescoping sum problem is we're going to be able to isolate for s sub n and take a limit. So let's first do a factoring step. S sub n, the nth partial sum, can be factored from these terms, leaving 1 minus r. The right-hand side is, well, I guess we could do something. Let's leave it the way it is. It's fine. So let's leave it in that format. We're solving for s sub n, so we can divide by 1 minus r, but notice that already r cannot be 1 any longer. If we did that, then there'd be no notion for s sub n. So s sub n exists as a partial sum in this format, provided the common ratio r is not 1. But any questions to that step? So now we have a limit that we can take. Now if you look at the telescoping sum problem that we ended on Thursday, this was essentially the same sort of steps that we've done, except we had to produce a second list to provide cancellations. So we take s sub n, we can now write this is the limit as n goes to infinity of 1 or a minus a times r to the power of n divided by 1 minus r. So this is not a terrible limit because the index for the limit is variable n. The only thing that depends on n is this right here, the r to the power n. So if we determine what the limit of r to the power n is, essentially the problem is over. Would you folks agree with that statement? Okay, so let's look at that limit. We want the limit as n goes to infinity of a times r to the power of n. But a is constant, so this really reduces to a times the limit as n goes to infinity of r to the power n. And remember, r cannot be 1, but now if we go back to some of the notes we did last time in section 11.1, we had a really interesting theorem that allowed us to look at exactly that type of limit. So let's go to the 11.1 notes as a refresher, since this was a long weekend for me as well. And somewhere down here, somewhere down the line, is what we want. We want to take the limit of r to the power n, and this theorem, number 9, tells us if r is less than or equal to 1, or bigger than negative 1, then it will converge. So we can say the limit of r to the power of n will be 0 precisely when r is between negative 1 and positive 1. The limit of r to the n would be 1 precisely when r equals 1 itself. But we cannot allow r to be 1 in this situation because of the format for s sub n. So this is when we get a value for that limit. Right on this line with that condition. Does that make sense so far? Okay, so we can say that if the absolute value of r is less than 1, or if you prefer, that's no different, but it takes longer to say, if r is between -1 and +1, then the limit as n goes to infinity of r to the power of n, a times it, would be equal to a times 0, which is 0, by the theorem 11. And it also tells us if absolute value of r is bigger than 1, then a times the limit as n goes to infinity of r to the n does not exist. Okay, so that's where we're at so far. I think we need to kind of maybe paraphrase what we've all done to this step. But any questions or comments first? Okay, so let's say where we're at and what we're doing, why in the world we're doing it. We're trying to determine the convergence or divergence of this. It all depends on r, really. Then we said this would be the associated sequence for the series. The formula for the partial sum, the nth term, would be by this. And we need to take that limit. We found by a bit of algebra over here that it turns into this. And now we can say that if the absolute value of r is less than 1, the limit of a times r to the power of n is 0. And it becomes equal to, in this precise condition, a divided by 1 minus r. So that's the limit of the sequence of partial sums, provided the absolute value of r is less than 1. If the absolute value of r is greater than 1, or if r is equal to 1 itself, then we have big problems. Well, r better not be 1 because of this algebra here, and other problems are if the absolute value of r is bigger than 1, then this would not exist. In fact, we can be a little bit more specific. If it's bigger than or equal to 1, it would not exist. So let's wrap all that together and conclude that problem over there. Questions first?
Yeah, so how are we supposed to know that r times s of n is going to cancel most of the...
Well, if you look at this a little bit closer, I think I did skip a step right here. If we write s of n, negative r times s of n, the list would really look like this. First s of n is a. Let me put this maybe in red just to highlight this extra missing step. We have a plus ar squared plus all the way to 8r power n minus 1. So all that would just be the Sn portion. But negative r times Sn would be all of these terms here with a negative sign. So you could take this, go minus ar plus ar squared plus ar to the power of n itself. However, once we distribute the negative signs through, notice that the ar's would cancel. However, a itself would survive because no term inside here has a to the power, r to the power 0. Then ar squared would also cancel all the way up to a to the power of r minus 1. Let me add that bit there. A to the power of a times r to the power of n minus 1 plus ar. There'd be a cancellation from here to here. So the only survivors are way out here a, and way out here a times r to the power of n. Does that make sense with that? Cool. That's essentially what we did with the telescoping sum problem on the end of Thursday as well. Other questions or comments about that? Okay, so this is really fortunate. The specific type of series, which we're later, or very, very shortly, going to call a geometric series, has partial sums, S sub n, for which we can actually solve and take an interesting limit. This is actually really, really rare. Finding a formula for S sub n for which we can take an easy limit is not straightforward to do in general, but at least we could do it this time. So let's summarize using this definition what our formula is. Other questions so far?
I guess,
Yeah.
how did you cancel out the Rn in the very last step?
Right here,
Yeah.
we used this limit right here. We want to take the limit of a times r to the power n, because
Oh.
that's the only feature that actually depended on n. In other words, the limit can be the limit of the numerator divided by the limit of the denominator, but the 1 and negative r and a were all constants. So we use theorem 9 directly on r to the power of n to say if the absolute value of r is less than 1, then the limit comes out as 0 itself. Kind of a nasty problem because steps are all over the board though. What other questions about it so far? Okay, so now we're ready to summarize, and the way we summarize is through this definition. We're concerned about some series, different than this one. The convergence or divergence depends on the limit of the partial sums S sub n. And that's precisely what we're looking at right here. So let's wrap all this together and come up with a formula. We can call this the geometric series test. For our first, oh, that was a perfectly fine piece of chalk. But let's call this the geometric series test. So this is our first test for convergence, divergence of series. We're going to get well over a dozen on the very end of the chapter 11. So really the major strategy here is to organize what makes something a geometric series. We say a series of the form, oh, very brittle chalk today, I goes from 1 to n of a times r to the power n is a geometric series with what we call the common ratio r. And by taking that limit and discussing when the limit exists and does not exist, we've in fact determined precisely when the series converges and diverges. We'll write on the next sentence, the series converges if and only if the absolute value of r is less than 1. Meaning if r is anything other than the values between -1 and +1, excluding the endpoints, the series would diverge. So if r is equal to 1 or larger, if it's equal to -1 or smaller, we have divergence. So this tells us precisely when it converges, but there is more. In the case it does converge, notice we were able to look at the limit of partial sums. It would converge to that exactly. So we can say, if the common ratio of r is less than 1, then the series, as I goes from 1 to infinity, of a times r to the power of, again, this is critical, it should be a -1, or else it would be a different formula. This would be equal to a divided by 1 minus r. Let's say if r is less than 1, we do have convergence by the previous sentence, and this is the sum of the series. So that's our new test so far. Any questions to this stage?
I guess,
Yeah.
how are we gonna be able to determine R? Like,
Oh,
are-
in an actual problem, we just get one.
Oh,
So
okay,
like,
cool.
we might have a third and 0.3 to the power of n.
Oh, okay.
Something like that. In this problem, it was nasty because we did not know the value of r, so we had to work in full generality.
Okay.
What other questions so far about the formula here? Okay, let's do that just next like you suggested. We're going to get geometric series and determine if they converge, diverge. But really, what makes all of chapter 11 nasty is if I make some small changes to that as a series, it's no longer geometric. And there's going to be a different test to determine convergence, divergence. So what makes it geometric is the r is constant as a base. The exponent n varies. If the exponent varies and we have a constant base, that would be a geometric series. If we switch that, if we had n to the power of r, it would be something else. We would call that a power series instead. And the determination of convergence, divergence is completely different. So those things maybe are not completely important right now, but they become really the most critical thing down the line when we have to deal with all the tests all at once on exam 3. But then, any questions before we try some standard problems using this as a formula? Okay, let's give it a try then. So the instructions for these kinds of problems go along these lines. They'll say, determine the convergence or divergence of the series. But just like on the homework assignment that's due on Thursday, there are certain expectations on the type of work and the type of bookkeeping and notes that we want to attach on a full solution. So the LESS problem tells us to show correct real limit notation throughout the process. That's still the case here, but we also have to do a little bit more. And this is the type of instructions you'll also see as an exam problem as well. It would say, show all necessary steps of the chosen test. So that seems appropriate. And I mean that we are going to have 2 tests, so there's not a lot of tests, but it's also going to say, also state the conclusion and the name of the test used. So that's an extra bit that we'll also have as a set of instructions on the problem. So for example, if a different problem asks for maybe the test for divergence and we use that test, just state at the very end, diverges by test for divergence. Then one more bit of instructions. This last bit of instructions is kind of unusual because this is actually very, very unusual. It's not too common to actually be able to say what the exact sum of a series is. In general, that is a very difficult mathematical problem. But if it's a geometric series, we do know its total sum provided it converges. So that's the last portion of the instructions. If the series converges, then find its sum. We'll see after exam 2 when we're doing exam 3 type problems, that last sentence is kind of unusual. But we're ready to start. And the type of problems you might see on, say, the suggested problems for practice or an exact exam problem would go about like this. Summation as n goes from 1 to infinity of 9 to the power of n divided by, let's go with, say, 10 to the power of n minus 1. Okay, so one problem with these types of geometric series are that there is a bit of algebra that we have to attack first. What we're trying to get at is this format. I want some constant a that does not have an exponent depending on n, and I need something to the, oh no, that's a terrible mistake, something to the power of n minus 1. Correct down there. That should be revised to n minus 1. Put that in red. So I need to get exactly to that format. We definitely have a geometric series because the bases are both constant, 9 and 10, and the exponents vary with n, the n and n minus 1. So I like the n minus 1 here, but my first step, I'm going to take 9 to the n, divide by 10 to the n minus 1, and do this. Let's go 10 to the power n minus 1. 9 to the n can be factored as 9 times 9 to the power n minus 1. So we're doing a bit of preliminary algebra before we get too far with the series itself. Any questions to that step? Okay, by laws of exponents, you could say this is really 9 to the power of 1. These would combine back to 9 to the power n. Next thing we can do by the law of exponents is say that this is the same as 9 times. We can take 9 over 10 and raise it to the power of n minus 1, because that power n minus 1 would distribute to the numerator and denominator to get back 9 to the power n minus 1 divided by 10 to the power n minus 1. And we do have a 9 that's left over, but that's our a in the formula over there. Any questions to that step with the exponents? Okay, so with this all set up, we can say that this is equal to the sum as n goes from 1 to infinity of 9 times 9 over 10 to the power of n minus 1. And now we can say that this is a geometric series with the common ratio we indicate by r. What would r be in this problem? Is it 9 tenths to the power n minus 1, or all of it? All of it's kind of a bit much. What would you say r is in this problem? Exactly. R itself is 9 tenths. And I would say that that is less than 1 as further work on this. The reason I'd like to say that that's less than 1 is because it takes me to this. I don't need the absolute value because I have something positive, but we have something that's between -1 and +1. We're told by the test that that is precisely when we have convergence. So we can say the series converges. Any questions with that last step? We've done not a whole lot of writing. We've manipulated the terms into a format that we recognize for the geometric series formula. But notice we've also, along the way, let's see here. We've shown all the necessary steps of the chosen test. I would say that's working this out and finding the common ratio r, saying it's less than 1. So that would be something that's required on your problem as well. It says, state the conclusion. That's what we did over here. It converges, so that's part of our conclusion of the problem. The instructions also say the name of the test used, and we said somewhere geometric series, so that would be fine. Or you could have rewritten this as r is 9 tenths, which is less than 1. The series converges by the geometric series test, and that would be fine as well. Just mention somewhere that you're using the geometric series as a test. If you just said this is a geometric series, I'm assuming you're using the test anyways. So we've done just about everything. Last thing to do is find its sum once we know it converges. If it diverges, it has no sum and we would just stop. Any questions so far? Okay, there are word problems because there is not a great deal of math that we're actually doing, but there's different features on how things are graded. So make sure that you do show the work with working out the exponents. Tell me what your common ratio r is, and I just did this so I can match the right conclusion, and be sure to specify what test was used. Again, there's 2 tests on exam 2, so there's not much to pick from, but there's going to be like a dozen tests on exam 3, so that becomes just a good practice down the line. So now we're going to do the last part, find the total sum. We can say by the test down there, that this would be equal to a divided by 1 minus r. And notice we've already specified what r is. It's 9 tenths. The a value is the 9. So we have a formula. We can directly evaluate it and say not only does this converge, but we, very lucky in this problem, say exactly what it converges to. The numerator would be 9. Denominator would be 1 minus the common ratio, which is 9 tenths. And supposing that you are taking this as a real problem on exam 2, and you just have other problems to get to, if you stopped right there, that's forgivable because the calculus really ended at that step. Let's keep working it out. You could convert 1 to 10 tenths. Say that this is 9 divided by 1 tenth, or 9 times 10 onths, which is a weird way to say 90. And that's what the series would converge to. And if you like, you could get onto Excel in the same way we did and watch as the terms actually approach 90. You have to approach it really quite fast, so you won't need thousands of rows. Any questions with that kind of problem? Okay, so that's what the kind of steps look like, whether you're using a geometric series test, a p-series test, test for divergence. Those are the common elements, where the getting this equal to 90, all this work right here, was relative to this portion. If the series converges, find its sum. Let's try another one just for the sake of practice. Let's let this one be something like the summation as I goes from 1 to infinity of, let's do, how about pi to the power, or excuse me, pi divided by e to the power of n minus 1. So I like this problem quite a lot because there's no algebra to do, right? We already can say a in this problem is a 1. The common ratio r is equal to pi divided by e. So there's no real algebra to do. But we do have to decide, would this hold in our situation? Is the common ratio r less than 1 in absolute value? Or just less than 1 since it's positive?
Let's use this approximation again.
E is about 2.7, and pi, this is a horrible approximation, about 3.1. Is this good or bad for our cause then?
Bad.
This is really, well, I mean, it depends, right? I
Oh,
mean, it's
yeah.
bad for the sake of convergence, it's really bad.
Yeah.
This would be divergent. We have the common ratio r, I'm not sure what it is, but it's bigger than 1. That's not a great exam problem because I don't want you to have to worry and possibly forget these constants. But it's a neat little problem where as soon as you found that r is bigger than 1, you've done this portion of the work, there was not a whole lot of work to do, and we can say the series diverges. So that's part of the conclusion. So we didn't do a whole lot of work, but we've indicated that what the common ratio r is. We said it's larger than 1, which implies divergence. And a best practice that is necessary on exam 2 and becomes very, very important on exam 3 is state the name of the used test. So we can say the series diverges. Now if you just said geoseries test, or by the geometric series test, or something kind of terse and brief like what I just wrote, that would be the entire process for that problem. As soon as we know it's geometric, the common ratio is larger than 1, just say diverges by the geometric series test. Now we've done everything on that one. Much, much less work than the convergent case. Any questions about that one? Should we try another just for the sake of practice? Okay, let's do one that converges because that's where a lot of the work goes into these. I guess we'll find out if it converges. So this time a bit of a longer problem. Goes like this. It's the sum as n goes from 1 to infinity of 6 times 2 to the power of 2 times n minus 1 divided by 3 to the power of n. Okay. I'm not sure what will happen with this one, but we'll find out shortly. But again, most of the work is going to be in getting this to the right form that matches the formula. So I just need one common ratio raised to a power. We have a problem where the powers based on the index n are in 2 different locations. So I would start by just taking 6 times 2 to the power of 2n minus 1 divided by 3 to the n, and just work on it algebraically until it looks essentially like this. This is what we need if we're going to use the geometric series test. That's the only test we have really, so we're definitely going to try to do that. Next thing I'd want to do then is 2 to the power of n is problematic, so we need to fix that. Let's write this as 6 times 2 to the power of 2n minus 1. Could be rewritten as, say, how about we could go 2 to the power of 2n, and let's also go 2 to the power of 2 times n minus, oh, this is terrible, a half. How does that look to folks? What I'm trying to do on this one is, let me explain the my thought process, is I have something of this form, essentially, a to the power of m times n. I'm trying to get back to this. A to the power of m, I want my n here, and eventually n minus 1. So I'm using this as an exponent law, but in reverse. The thing I have to check is that this, in fact, multiplies out to the thing I needed, 2n minus 1. So I'm trying to split this into, n minus a half times 2 would be 2n times negative 1/2 times 2. Yeah, that would be 2n minus 1. Not a huge fan of the negative 1/2, but we'll get there when we get there. Any questions to that stage, however? So at least I took care of the 2 times n. We cannot allow that if we want just n minus 1, so we're breaking it down in stages. Does that make sense why we wrote that out in that form? So I guess you could say as a shorthand to what we did as a step, if I need to have just n, I essentially put 2 to the power 2 here, but all the terms 2n and minus 1 had to be divided by 2 for this to work out correctly algebraically. Now the power of 2, the power of n times n minus a half, would multiply back out to 2n minus 1. So at least we haven't broke anything algebraically. 3 to the power n also has to be corrected, but that's enough for one step. Let's go on to the next. So on my next step, we have 6 times 2 squared is really just 4. It's raised to the power of n minus 1/2, which again is a bit problematic because we need minus 1 specifically, but we're getting there. 3 to the n, we can use as the usual trick, 3 times 3 to the power of n minus 1. 3 to the power of 1 itself would be added to the powers n minus 1. We get back to power n, since those exponents would add up. And that's the hint on how we're going to try to correct this. We need to factor something out to get power negative 1. But questions to that step? It's kind of a horrible one, but we're getting through it. This would be a really nasty exam problem, but it's really good for the sake of practice and showing up the various techniques we have to use to get through this. Next step I would take is, let's just do a division, makes it look better. We have 2 times, we have 4n minus a half, but remember we need to make this n minus 1. So I need 4 to some power, let's just put a question mark there and resolve it in the next step. Put in what we need, 4 to the power of n minus 1, and I need to have the unknown power with the question mark added to n minus 1 to make it come out exactly as n minus a half. So what would you say the unknown power should then be? Should be exactly a half, exactly. In other words, if we take the root of 4, then 4 to the power of a half times 4 to the power of n minus 1 gets us back to this, which gets us back to this, which was part of the original problem. So that's some horrible exponent law kind of stuff we have to deal with, but we're getting there. It's divided by 3 to the power of n minus 1, and this is essentially your goal. If you want to get one common ratio to the power of n minus 1, we have to manipulate everything with an exponent n until it's n minus 1. The manipulations here were just kind of nasty, but next in the numerator is 2 times the root of 4, so we got 2 by 2. 4 to the n minus 1, 3 to the n minus 1 becomes 4 thirds to the power of n minus 1. So what does that say so far for this series? What is its fate?
It diverges.
It's diverging. All that work for divergence, darn it. If it was 3/4, this is what I would have done in the next step. I would have said the series itself would have been equal to, we have a 4, 1 minus 3/4, and we would have worked from then on. But in this case, the common ratio r, we can say here to summarize, so r is equal to 4 thirds, which implies the absolute value of r is bigger than 1. The series diverges, or is divergent if you like, by the geo test. If you start making these really, really brief geo tests for the geometric series test, I'll know exactly what you're referring to, and that's a decent shorthand, whether it's homework or exams. Any questions with that one? Okay, so that one diverged, which is too bad. The reason things are diverging is 4 thirds to a power just grows larger and larger and larger as the power n gets ever larger. So if we're taking and adding infinitely many terms, things in those terms should not be getting larger and larger and larger. Would folks agree with that? In other words, if this did converge, the terms themselves should be getting smaller and smaller and smaller, approaching 0 in the limit. Do folks also agree with that? Awesome. That would be an entire theorem, which we'll skip the proof on, since folks seem to believe it, but the book would cover that proof, I believe. So let's state that as a theorem. It's not a test, so where should we put it? Maybe over here. We'll state a test very next. So we're going to have two tests on this exam. First is geometric series tests, where when we find convergence, we use the find the total sum. This one is a theorem from which we'll get a test. The theorem says the series, or it says if the series, which is a summation as n goes from 1 to infinity of a sub n, so just a generic series, if it converges, then we agreed the terms in the sequence should be getting smaller and smaller and smaller, tending towards 0. In other words, if the series converges, then the limit as n goes to infinity of a sub n must be 0. So that's our statement. It's essentially saying if I'm going to add infinitely many terms, those terms better be coming closer and closer to 0, and they need to be getting closer and closer to 0 awfully fast, because we found last class, and the book proves, the summation as I goes from 1 to infinity of 1 over n, this was our harmonic series, and this diverges. So this is divergent, harmonic series. Okay, so that's our theorem. It's really just a statement of what our intuition is saying about adding infinitely many terms. But we can take that theorem and come up with a new test called the test for divergence. It is the test. If you suspect something diverges, you really ought to be thinking of this test. It fails often. In other words, it doesn't always meet the hypotheses, like in this case. And to discuss what's kind of going on there, let's look at some statements in a form of an implication. So let's say let P and Q be two statements, or propositions. Let's go with statements. Then we can say if P implies Q is true, then it's contrapositive is true. The P implies Q is essentially the format of the theorem that we just wrote. You could say if P, read this as then Q if you prefer. So here, if the series converges, all of that is the P portion of the statement in this theorem. Then the limit as an equals 0 is the Q's portion. So if we look at if P then Q, if this is true, and it is true, that's a theorem that seems true by intuition and can be proved, its contrapositive is true. So let's write the contrapositive. The contrapositive is not Q, or the negation of Q, implies not P. So that's the full contrapositive. So knowing what P and Q is in the prior theorem, test for divergence is simply the contrapositive of that theorem. So let's write that out next. Any questions first? Okay, the contrapositive says we are going to take the conclusion and negate it. Not Q is the first portion of the contrapositive. So we'll say, oh darn it, I know, I need to probably just hide these away so I have good ones not being harmed. But if the limit as n goes to infinity of a sub n is not 0, in other words, not this statement Q, then what would you say the conclusion should be? What is the not P portion of the contrapositive? Well, P was the statement the series converges, so what should not P be? The series
Diverges.
would diverge, correct. So that's the full contrapositive. If the limit of this sequence, which we spent all the time in 11.1 working on, is non-zero, then the series summation as I goes from 1 to infinity of A sub n diverges. So that's our good old test for divergence. This test gets used very, very extensively throughout the entirety of chapter 11. So it's a great one to always have at the ready. It'll be on exam 2 and exam 3, as well as the geometric series. Geometric series may not be emphasized as much on exam 3, but this one certainly will. One thing that's sad, however, is that the converse of P implies Q is Q implies P, and it need not be true. This is actually quite sad, and that's what's going wrong with the harmonic series. The converse is that the limit of 1 over n is 0. However, the harmonic series does not converge. That's the statement here. If the limit is equal to 0, the series converges. That is patently false, and this is the counterexample. Harmonic series does satisfy that the portion here is true, but we cannot reverse the logic. If we could reverse the logic, we would have used an if and only if in the packaging of this theorem and in this theorem down here. But those are the things to watch out for, and let's take a look at a couple problems that's going to use test for divergence. Any questions first?
Question.
Yeah.
What is the harmonic series?
It's this series right here that involves the 1 over n. That's a kind of an interesting series because it looks like it converges, but if you look carefully, the book proves it on 11.1, it's truly a divergent series, which is very surprising. And in 11.3, we'll investigate another proof of why that would diverge using an integral test. But other questions about this so far?
So are we
Yeah.
only going to need to know the harmonic series for the divergence test?
We would not have to know it for the test, no.
Oh, no? Okay.
Yeah, it's just a counterexample of why you cannot reverse a logic over here.
Okay.
This would be a reason why it can't quite work in general. But other questions about that? Okay, so with the exact same instructions, that's essentially how I'm going to write the exam 2 instructions for 11.2 problems. Let's look at other series. So first one we can look at is, how about test this thing for convergence divergence. As n goes from 1 to infinity, we're going to sum all terms of n times n squared minus 3 divided by n cubed plus 4. So we want to test this for convergence divergence. And really there's two tests. Would you say this is a geometric series?
No.
Definitely not. For a geometric series, n must be an exponent in every portion of the sequence. N is a base, so that's a different type of series. However, if it's not the geometric series test, this only works on exam 2, we should be able to use the test for divergence. So let's give that a try. If we want to use the test for divergence, then we need to take the limit as n goes to infinity of n times n squared minus 3 divided by n cubed plus 4. But keep in mind, this is a rational function, and we've said as a standing set of rules in this class for grading, if you have a rational function and you can just see the limit, you can state it without work, and that would be A-okay. Question first?
Can you look at the front coefficients to like the n? So there's like an n cubed and n cubed, can you just look at the front?
Exactly, yes.
Okay, sorry.
So what would be the limit of this thing then? It would be exactly 1. But how do folks feel about that? Does that make sense?
Could you go over the M and N rules really quick?
Yeah, absolutely. So if I wanted to work this out step by step, first I could take one step and distribute n through like you suggested and get n cubed minus 3n divided by n cubed plus 4. Then there's still other steps you could take, but if there is a tie on the exponents, the highest exponents in the problem, when we're comparing numerator and denominator, we have a tie with degree 3 on top, degree 3 on bottom. We just pull the coefficients in that limit, which would be 1 over 1 for a limit of 1. So it's showing an extra step. It's not the book's official method, but this is a rational function with horizontal asymptote y equals 1. So if you go back to chapter 2, that is a bona fide theorem that says the limit must be 1. But there's still other algebraic steps we can take if we're not completely sure. Should we try it a different way, or does folks feel okay about this version? Okay, the other thing the book would do is go to the denominator, take the term with the highest power, divide everything by n cubed. If you did that, it would look like this. So this is a third way to do the same limit. You would get divide n cubed here, it'd be 1. Divide n cubed here, it'd be 3 over n squared. Divide it here, we get 1. Divide n cubed here, and it's 4 over n cubed. But in the limit, these two would go to 0, and it would still be 1 over 1. But if you can look at a rational function and just see a limit of 1, this is considered acceptable work. And this is 3 versions of working it out. But in either case, we have limit 1. So we go to the test for divergence, and it says if the limit is not 0, in other words, the limit could fail to exist, it could be infinity. If it is not 0, series diverges. So the problem is over. It's really fast, in fact. We can say diverges by the test for divergence. And that's the full set of work on this. Any questions about that? Again, test for divergence becomes massively dangerous once we get in sections 11.3 through, say, 11.8. Because if we look at this divergent harmonic series, it is true that the limit, as n goes to infinity, of 1 over n is 0, but this is not the hypothesis of anything in this theorem or this theorem. This is the conclusion in the theorem. It is not the conclusion in the test for divergence. So this tells us nothing at all. If the limit is 0, this gives no information about the convergence or divergence of the harmonic series, which is a series as n goes from 1 to infinity of 1 over n. In other words, we might say the test for divergence has failed. And that could either converge or diverge. In fact, diverges. So you have to be very, very careful with this test. In the test for divergence, that is the hypothesis. If that's met, then you can conclude then it diverges. But this is a horrible situation that comes up quite a lot, and it means you'd have to pick a new test. Other questions about that? Okay, let's see. How about one last one, and then we'll call it a day. Does that sound all right to folks? Okay, so this next one goes, we have, well, there's so many good ones to pick through. How about the sum as n goes from 1 to infinity of e to the n divided by n squared. So first we have to decide, is it a geometric series? If it is a geometric series, this is definitely the better test. So what do folks say about this one?
No.
Yeah, it turns out it's a no. It almost looks good so far because e is a constant, or n is an exponent, but as soon as n manifests as a base in just one position, whether it's raised to an exponent or not, this is not geometric any longer. So this is not a geometric series. But that's okay. That means we go to the only other test we have, test for divergence. And in the test for divergence, we investigate the limit as n goes to infinity of e to the n divided by n squared. What would you say the limit of this ought to be? It's one of those weird situations where the numerator is tending towards infinity pretty rapidly, and the denominator is tending towards infinity rapidly still, so it's an indeterminate form, which means we'll just hit it with L'Hopital's rule till it becomes determinate. What we could do is define a function f of x, which is the continuous analog of this discrete function, but you'll notice that once you do that and you take the steps in L'Hopital's rule, algebraically you're doing the exact same sequence of steps. It's really just whether you use the variable x or n. So you can, as a shortcut, apply L'Hopital's rule just immediately, and I would say that's okay. I'll put an h here to just indicate the reader. I've used L'Hopital's. Say that this is the same as the limit of e to the power of n, visualizing it as e to the x. So we get e to the n down below and take the derivative of n squared, which would be 2n. It's still infinity over infinity, so we just hit it with L'Hopital's as many times as necessary hoping we don't hit an infinite loop, which is sadly possible. I wouldn't do that on an exam though. So the limit of the numerator is e to the n. The limit of the denominator, or excuse me, the derivative of the denominator is 2, and the derivative of the numerator is still e to the n. So what would be the value of the limit at that stage?
Infinity.
Yeah, we have something that's constant, numerator grows without bound, so the limit is infinity. So the test for divergence says, if the limit of a sub n is not 0, well, this is not even a number, it's not a symbol. Here, you could also just say further for clarification, if the limit also just does not exist, that certainly qualifies with this case, then the whole series diverges for test for divergence, or by the test for divergence. So the last thing I would have to do to get through these list of criteria in the problem is say, it diverges, so that's our conclusion. Always make sure you've thrown the conclusion in there somewhere. And it asks us to name the test. I would just say test for divergence if I want to abbreviate it a bit. So divergence by the test for divergence. I forgot a word. It's bugging me. Divergence by the test for divergence. I forgot article. But that's okay to be a little bit terse on an exam especially. Any questions with that one? Questions people often have is, well, the geometric series test fails on this one because the limit is 0. What then? Well, we could copy the Book's method to determine the convergence divergence of this, but that was a very ad hoc proof that they gave, and it would not carry over to something like this, say, in a very nice way. So at 11.3, which is going to be after the exam, will give us further methods for when the test for divergence fails, and we do not have a geometric series. But that's essentially the scope of the exam for 11.2. You should be ready for geometric series, the case it diverges, the case where it converges, where you have to use the formula that got deleted, and you should expect a problem with the test for divergence as well. Any questions, folks, then, before we call it a day? I think we went over a little bit, but we'll try to cut it short, maybe go to, oh, we shouldn't cut it short on the review day, that's horrible. Well, I'll make it up to folks somehow, some way. If you have questions, feel free to stick around as usual. Oh, and if you didn't get your homework, I should have it.